Okay, welcome back here. Let's look at these questions we have about our diagram that we already have. So now hopefully everyone's got the right diagram. Even if you drew it incorrectly before, you've got the right one here. So second question here says, which force is greater, gravity or the normal? Explain how you came to your conclusion. Well, we've already answered this, right? We've said that the normal and gravity, or the weight I'm calling it here, those have to be the same. And I came to that conclusion because it's not moving down or up. So no one's winning that war, and so they must be equal and opposite to each other. Using that same logic, but a little bit more complicated, is question 3. Which force is the greatest? Tension, Chris's push, or friction? Explain how you came to your conclusion. Well, friction's got to be the greatest force here. Why? Because friction alone balances out the tension and Chris's push. So tension plus Chris's push equals friction. So that one's got to be the longest. And also I've indicated that already by drawing it 3 blocks long, and this one 1, and that one 2. And again, you might be like, how did he know to draw it 3? I made it up. I could have drawn tension 2 blocks and Chris 2 blocks and friction 4 blocks. But I know that the friction's got to equal those two together. And so finally here it says, which forces in your diagram require direct contact and which do not require direct contact? Well, almost all of them require direct contact. So tension is direct contact. You got to be in contact with the rope there. Chris has to be directly pushing on the block right there. A normal force, you can't have the ground push up on you if you're not pushing down on it. Friction, you can't have the ground exert friction on you if you're not scraping up against it. The only one here that doesn't require direct contact is weight, or the force of gravity. So even if you were up in the air and you drop that block, clearly gravity reaches through space and grabs it and pulls it back down there. All right, so now we got a bunch of these free body diagrams to do. We'll do these relatively quickly now that we see how to do them. So we got a book right here, and the book is just sitting on the table, and they want you to do a free body diagram. So this is kind of like the block, but just simpler. We've got the force of gravity, or weight, I'm gonna call it, down. And then we've got the normal force of the table pushing back up on the book, up like that. And so what evidence do you have for the existence of your forces? Well, it's here on Earth, so we know there's weight on it. And it's pushing into the table or whatever this is, and so that's got to be pushing back up on it. So we know there's got to be a normal force as well. And what observation can you make that allows you to determine how the magnitudes of the forces compare? Well, it's not moving, so these two forces must balance each other out. They must be equal and opposite there. So now they get a little bit more complicated than this here. And we put a bigger book on the lower book, and they want us to do 2 free body diagrams here. So one for the upper book and one for the lower book. So the upper book, 1, 2, 3, also has weight. I'm gonna draw it bigger than the previous one. I drew it 2 blocks down for the lower book, so this is a bigger weight. So I'm gonna draw it 3 blocks down. And then it has a force on it too. It's the lower book pushing up on the upper book, but that's also just a normal. Any time 2 surfaces pressed against each other, it's just a normal force there. So what about the lower book? A little bit more complicated in this case. We know that we still have its weight down, right? I'm gonna keep the same that I drew it on the previous page. So weight down is 2, let's say. And then we've got a force of the upper book pushing down on it. So the upper book pushes down on it. 1, 2, 3, I'll draw that down. So what would we call this? Well, it's a type of normal. It's the normal from the upper book, right? The upper book is pushing down because there are 2 surfaces on the lower book. So it's getting squished by the upper book and gravity's pulling down on it. So what is the next force there? Well, we gotta have a normal from the table or the ground, or whatever you wanna call it. It's beating both of these forces. Whoops, I've created a little bit of a problem here, but this one's 2 blocks long, this one's 3 blocks long, so 1, 2, 3, 4, let's just pretend that's 5. So this would be the normal from the ground or the table, whatever you picture as pushing up on that lower book. And let's get to some questions then here using these diagrams. So it says, explain why a force that appears on one diagram should not appear on the other one. And it's this one right here. It's this extra normal force. It's because the lower book is being sandwiched, right? So the lower book is sandwiched. It's between two surfaces. And so it gets two normal forces on it. What type of force does the upper book exert on the lower book? Well, it's two surfaces pressing together. So it's a type of normal force. Some people want to call this a weight. They say the weight of the upper book's pushing on the lower book, but that's not true. This thing experiences its own weight, so it's a type of normal force there. Which of the forces is greatest in magnitude on the lower book, and how do you know? So out of all these three, the normal force from the ground's got to be the biggest. Again, how do I know? Because this one force balances these two other forces. So it's got to be the normal from the ground. Which force changed on the lower book when the upper book was added, and which forces stayed the same? So the force that changed would be the normal from the ground, because before, let me get this one back out. When the lower book was just sitting there by itself, I only drew it as 2 blocks. Again, I arbitrarily chose that, but because it only had to match its own weight, the normal from the ground. But now it's got to match the weight of both the lower and upper book. So this normal force from the ground changed on the lower book. The one that didn't change is the weight. It still weighs the same as before the lower book. Some people are like, no, it weighs more because of the upper book, but it still has its own weight. Gravity pulls down on the lower book just the same as it did before.